Namaste. Welcome back to Murali's World of Physics.
Consider the following situations from real life. A car running on the road and its eventual braking at a stop. A man walking along the road. An aeroplane on a scheduled flight. A bird flying in the air. The lighting of a matchstick. Hugging of a hand. Dragging a block of wood on a table. A boy trying to push a heavy box along the floor, etc. Now the question is, what is common among such apparently uncorrelated situations? Well, it is the forces of friction that manifest in all the above and similar situations. In today's video, we will be discussing the physics of frictional forces.
Well, what is friction? It's a type of force that comes into action when two surfaces in contact try to move against each other. So in this case, it's an automatic force being exerted between these two surfaces, and this resists the motion. For example, suppose we have a block of wood kept on a tabletop and we try to push it. For some time it will not move. Thereafter, when the force is somewhat larger, it starts moving. So the initial time when there is no motion, there is actually a frictional force coming into effect which opposes the pushing force, and therefore that almost balances the pushing force and there is no motion. But thereafter the pushing force overcomes the frictional force and the motion results. Obviously, for motion to occur, the frictional forces have to be overcome by the pushing force. Therefore, the pushing force P must be greater than F, the frictional force, in order that motion occurs. So when motion occurs, it can be either at constant speed or with an acceleration. So if there is an acceleration, then from Newton's law, the effective force acting on the object will be the pushing force minus the frictional force which opposes P. So therefore there is a net force acting on the object, and that should be equal to m into the acceleration, where m is the mass of the object from Newton's law. Now when the object moves at constant speed, of course these two will just balance. Well, that is the case at zero speed also, that is when the object is at rest. So the opposing frictional force should just balance the applied force. It's a characteristic of friction that it always works in the direction opposite to the direction the object is moving or trying to move. So when there is motion but still there is a pushing force, there is no movement, so the object is trying to move. So therefore friction always tries to slow down a moving object. That is something which we do not like occasionally. That means the motion in this direction is opposed by the frictional force in the opposite direction. Well, it is as if nature abhors relative motion between objects. The magnitude of frictional force depends on the nature of the materials out of which the two surfaces are made. For example, consider a smooth surface and a rough surface. So this is a smooth surface, this is a rough surface on which I keep my object and I try to push it. So on the smooth surface, a small push may be sufficient to overcome the friction and make the object move. So therefore in this case there is a low friction. Whereas with respect to the rough surface, we will have to push little harder in order that the object moves. So in this case we have high friction. Also, friction depends on any forces that press the surfaces together. For example, in the case of the book lying on the tabletop surface, this force would be the weight of the book acting downwards. That is the gravity pulling the book downwards. Suppose you consider a man running with a piece of paper on his chest. From our ordinary experience, we know that as he runs along, the paper will be kept stationary against his chest. So in this case there is air resistance, that is what pushes the paper and keeps it pressed against the chest. So that is the force which presses the two surfaces together. Well, if you consider an object on a carpet and an object on a wooden floor, it is obvious that we have to push the object harder to get it moving on a carpet rather than when it is on the wooden floor. This is because there is more friction between the carpet and the object than there is between the object and the wooden floor. Well, friction is a necessary part of life. We can't live without it. The world would be utterly different without it, and nothing would stay in place, and given the slightest push, nothing would stop. For example, friction between the tires of any vehicle and the road helps to drive safely and to stop it. Also, a rock climber relies on the friction between his shoes and the rock to make upward progress along the surface of the rock. I am listing some of the common features of frictional forces. The frictional force will be always parallel to the two surfaces in contact. And that is how it can oppose relative motion between the two surfaces. The magnitude of the friction force will depend on the material in contact. For example, the friction between rubber and concrete is different from that between ice and steel. Also, the frictional force is always in a direction opposing the motion. That means in a direction opposite to the direction of motion, and hence opposes the force which causes the relative motion between the two surfaces in contact. In all cases, the friction results in loss of mechanical energy, which of course reappears in the form of heat. So friction is therefore a non-conservative force. That means the work done in this case against the friction is path dependent. In the presence of friction, some kinetic energy is always converted to thermal energy. Hence, mechanical energy is not conserved, although the total energy may be conserved. In all instances of friction, another force is present inherently, that is called the normal force. The normal force is defined as the net force compressing the two parallel surfaces together, and its direction is perpendicular to the two surfaces. Well, this is two examples I had quoted earlier. So in one case it is the gravitational force which makes the normal force, and in this case it is the air resistance which forms the normal force. The frictional force will be of course related to the normal force, as we shall see slightly later. Now, Newton's third law implies that there is a reaction force equal and opposite to the above normal force. For example, the object on the table, we have the weight, the gravitational force of the object being applied on the table surface, and in return the table will push the object with an equivalent normal force in the opposite direction. So therefore, when the object is not moving or even otherwise, N will be exactly equal to W. So the magnitude is same as normal force and direction will be just opposite. The force of friction is found to depend on the magnitude of this normal force. If the normal force is more, then the frictional force also will be proportionately larger. Now, certain materials, especially liquids, have the special property of reducing the friction between the solid surfaces, and these are called lubricants. Typically, the lubricant to surface friction is much less than the surface to surface friction in a system without any lubrication. Thus, the use of a lubricant reduces the overall system friction, and some examples are motor oil, wax and grease. Well, we shall see little more details about this type of friction and lubricants slightly later on. Now, there are certain empirical laws of friction enunciated by Amanton and Coulomb. The first law is Amanton's first law, that is, the force of friction is directly proportional to the applied load, namely the normal force. Secondly, we have the second law, which says the force of friction is independent of the area of contact between the two surfaces. The third law states that kinetic friction is independent of the sliding velocity. This is the Coulomb's law of friction. Now, the first law, namely Amanton's first law, gives us a direct method to introduce an important characteristic property of the material surface with regard to friction, and that is called the coefficient of friction, and designated by the symbol mu. It is actually the constant of proportionality between the friction force and the normal reaction N. So the friction force is equal to mu times N, and it is seen that mu is for most materials less than 1. In other words, the more the normal force, the more is the consequent frictional force developed. Now, mu is found to depend only on the material. It is not a function of mass or volume. For instance, a large aluminium block has the same coefficient of friction as a small aluminium block. However, the magnitude of the friction force itself depends on the normal force and hence on the mass of the block itself. Now, mu is an empirical structural property. That means it is an experimentally measured structural property that depends only on various aspects of the contacting materials, such as surface roughness, adhesive forces between the surfaces, etc., etc. So here this is an illustration of Hamilton's second law regarding the independence of the frictional force on area of contact. Of course, provided normal reaction is same. That means provided the mass of the two objects are the same, the frictional force is independent of the actual area of contact between the object and the table surface. For example, here the area of contact is small, here the area of contact is bigger. But you find that if the masses of the two blocks are the same, then the frictional force F of 1 is equal to F of. Now, as far as the third law is concerned, which is also known as Coulomb's law of friction, it says that the friction when the objects are moving between the contact surface of the two dry solids is not affected by the magnitude of the relative surface velocity. That means how fast the two surfaces are sliding against each other. That is a material in deciding the kinetic friction exerted between the two surfaces. Now let us inquire the origin of the frictional forces. Now for this we have to go deep down to the molecular level of materials. Matter at this level is not as smooth on a surface as it appears to be. In fact, there is nothing as an infinitely smooth surface. When we go to the molecular level, there are microscopically tiny irregularities like bumps and dips or hills and valleys or dales, and deformations existing on all surfaces, however smooth they may be. This is a comparison between smooth and rough surfaces. But once you magnify these areas, you can see that there are irregularities existing on the surface of the two materials. So this is there are two objects 1 and 2 pressing against each other along a particular surface area. So macroscopically the surfaces may appear smooth. Now suppose I enlarge a small portion around the surface by using a very powerful microscope and I go to the molecular level, you can see that there are irregularities, in fact hills and dales on both surfaces. This is another picture of the two surfaces. So these are the molecules of the two materials, and you can see that there are irregularities. In fact, these form the hills and these form the valleys or dales. So therefore the hills of one surface may dip into the valleys of the other surface, and when one tries to move the two surfaces relatively, then you can see that the hills bump against each other, and then that causes a hindrance to the relative motion. So we have the applied force here trying to push the two surfaces in relative motion, and we have the friction arising because of the interlocking of the hills and valleys. Such irregularities on the surface get entangled, and that is what gives rise to the frictional forces. Also, the molecular attraction, namely adhesive forces between the molecules of the two surfaces in contact, these also tend to prevent relative movement between the two surfaces, and this also is partly responsible for the appearance of the frictional forces. In fact, the more the roughness, the more irregularities and more significant will be the interlocking and the resulting friction. The hills and dales on the surface prevent direct and perfect surface-to-surface contact, but in fact there is point contact. Due to the point contact, there exists a very high pressure at contact points. The high pressure leads to the molecules of the two surfaces at the point of contact getting sort of cold welded, and thus a bonding exists between the two surfaces in contact, and this prevents relative motion between the two surfaces. So we have the cold welded joints. Now when the two surfaces in contact tend to move relatively with respect to each other, these bonds or cold welded joints do not allow them to do so. If you want to create relative motion, then additional forces, external forces are required to break these cold welded joints. This additional force explains the origin of friction. In fact, the friction between solid surfaces is usually referred to as dry friction. So we will come to the case of friction involving liquids later on. If the two bodies of the same material are in contact with each other, their surfaces in contact have similar irregularities and therefore get firmly interlocked. Also, the intermolecular forces of attraction between the two surfaces of the same material are quite strong. Therefore, the friction between the bodies is large. On the other hand, if the two bodies in contact are of different materials, their surface irregularities are dissimilar and hence they cannot get firmly interlocked. So also, the intermolecular forces are not very strong. Therefore, the friction between the bodies is not so large. Hence, the ball bearings, which we will explain later, used in machines are made of dissimilar materials. Now, we can see that friction is what is known as a self-adjusting force. We know that friction comes into existence when the two bodies in contact have relative motion or tending to have relative motion with respect to each other, and it opposes the intended movement. When the applied force is 0, the force of friction is also 0 identically. If the applied force is slowly increased, the force of friction also increases in the same proportion up to a particular limit. This force is called the limiting force of friction, the maximum frictional force which is necessary just before sliding starts. Within this limit, the force of friction is exactly equal and opposite to the applied force. That is why we can call friction as a self-adjusting force. Now if we try to change the direction of the applied force, the direction of the force of friction also changes such that it is once again opposite to the direction of the applied force. So the magnitude and direction of frictional force depend upon the magnitude and direction of the applied force. Implies that the force of friction can be called a self-adjusting force. It does not have an independent existence. Only when there is an applied force, the frictional force also appears. So it comes into play only when the applied force produces or tends to produce relative motion between two bodies in contact. Dry friction, as we have seen, originates from a combination of surface to surface adhesion, surface roughness and irregularities, surface deformation, and also surface contamination. The complexity of these interactions makes the theoretical calculation of friction from first principles impractical. So therefore, one has to depend on empirical methods for analysis and development of the theory of friction. Now, we shall see what are the different types of frictional forces. The dry friction, we have static friction, kinetic friction, and rolling friction, and finally we have fluid friction acting between fluids. In static friction, there is no relative movement of the surfaces. Block being pulled, but it is at rest. So therefore, in this case, the frictional forces just oppose the applied force, and there is no acceleration and there is no relative velocity. Now, second is the kinetic friction, where we have a body moving at a particular speed or with an acceleration. Well, in this particular case, we have the aeroplane moving in the atmosphere. Rolling friction is the one where there is a rolling motion between the two surfaces. So we have static friction, kinetic friction, and rolling friction. Static friction, there is no movement. Kinetic friction, there is movement between the surfaces, and in rolling friction, there is a rolling motion. Static friction opposes the start of motion. Kinetic friction between objects when they are in motion, and rolling friction occurs when a rolling object rubs against a other surface. So the rolling motion is prevented or opposed. So this is static friction. We have the weight of the body, the normal reaction, the applied force, and the frictional forces opposing the applied force. So the motion is just going to start. So up to that point, F will be equal to Fs. Now sliding or kinetic friction is appearing when there is motion between the two surfaces. So here, where the forces are identically equivalent, but only thing that the applied force overcomes the frictional force, and F will be greater than Fk, and the difference in the two will appear as the force causing accelerated motion. And if F is equal to Fk, the motion will be with constant speed. In rolling friction, for example, we have a wheel. The wheel rolls forward. The weight of the wheel forms the normal force. Then there is the normal reaction N equal to W, and there is an applied force pushing the wheel forward, and the friction resists the rolling. So static friction comes into existence when the two bodies in contact have relative motion or tending to have relative motion with respect to each other, and it opposes the intended movement. With the applied force equal to 0, the force of friction is also 0. If the applied force is slowly increased, the force of friction also increases in the same proportion up to a particular limit, and it is this particular limit which is known as the limiting force of friction. And within this limit, the force of friction is exactly equal and opposite to the applied force. Limiting friction is therefore the maximum opposing force that comes into play when one body is just at the verge of moving over the surface of another body. Now, second type of friction is the kinetic or sliding friction. When one object starts sliding along the surface of contact with another, the contact points on its surface do not get enough time to lock into the contact points on the floor, in contrast to the static case. Therefore, less applied force is required to maintain the motion once it has started. Therefore, sliding friction is slightly smaller than the static friction. So this is a plot of the frictional force versus the applied force. So this is the maximum or the limiting friction, and up to the point where motion starts, Fs is equal to F. So we have a progressively linearly increasing trend in the plot, Then once limiting friction is reached and the force, applied force increases further, suddenly there is a moment and the sliding friction gives way to the kinetic friction, and thereafter friction will be constant. So if k is equal to mu k n, where mu k is another constant, here Fs maximum is equal to mu s into n. This is the static friction constant and this is the kinetic friction constant. So therefore the first part of the curve, the frictional force just matches the applied force till the limiting friction Fs max is reached. During the static friction, the surfaces are at rest with respect to each other, and hence the cold welded joints are stabilized and are quite strong. During the kinetic friction, the surfaces are in relative motion with respect to each other, and thus the cold welded joints are formed at one instant and broken at the other instant without giving any chance for the cold welded joints to get stabilized. Thus the bonds are weak, and less force is required to overcome kinetic friction than that required in the case of static friction. Hence static friction is greater than the kinetic friction. So that is represented in part 3 of the earlier graph. Now rolling friction is the opposing force when one body rolls over the surface of another body. So it is the resulting resistance to the motion that we call the rolling friction. So this is the case of rolling. So we have the object performing a rolling motion along the flat surface being moved by the applied force, and the frictional force develops and is in the opposite direction. Now the most familiar and important example is that of the wheel. In fact, this was one of the most important and revolutionary inventions of all times. The wheel is used in conjunction with the axle in such devices as potter's wheel for transportation in various kinds of vehicles, water mills, spinning wheels, gyroscope, turbines for power generation, etc. In this particular example of a cyclist pedaling along the road, we have the several forces which are indicated here. The main force acting is the weight of the cyclist and the cycle, the gravitational force, and the normal reaction to this is actually twofold, each acting on the axle of the two wheels, and they are in the direction opposing the weight, and the pedaling action gives rise to the applied force, and that keeps the cycle and the cyclist moving in this particular direction. And arising from these normal reactions, we have the frictional forces acting at the point of contact between the tire and the ground at these 2 points. In fact, there is friction also at the axis of the two wheels, and also the air resistance being applied on all surfaces of the cyclist as well as the cycle. Well, this is the case of a car running along the road. So once again we have the weight of the car, and that is divided equally among the wheels, and the normal reaction appears here. The driving force pushes the car forward, and this is the driving force which pushes the car forward in this direction, and the frictional forces appear in the opposite direction. There is also the air resistance. Now, particularly in the case of rolling, the ball bearings are quite important. What is a ball bearing? It is a mechanical device made out of a ring of small metal balls. What does it do? It helps to reduce rotational friction and support radial and axial loads. These metal balls can freely roll, made to make a machine's moving elements roll through each other instead of slide, thus achieving reduced friction, because the rolling friction is less than sliding friction. A ball bearing is placed between two surfaces that must roll over each other. These surfaces are commonly called races. Now each race is a ring with a groove where the balls rest. The groove is usually shaped so that the ball is slightly loose fitting in the groove and can rotate freely. The axle is attached to the inner side of the ball bearing, while the wheel is attached to the outer side of the ball bearing. So here we have a diagram. This is a set of ball bearings. So these are the races. These two rings are the races. These are the steel balls kept in the space between the two races. And to reduce friction further, we may add a lubricant also in the space where the balls are situated. So the inner ring is attached to the axle and the outer ring is attached to the wheel. These are typical values of the coefficients of friction. These are the different types of materials: cast iron on cast iron, glass on glass, leather on oak, non-stick coating on steel, oak on oak, steel on steel, steel on steel with castor oil with lubricant. So coefficient of static friction, well, these are the typical values, and you can see that the kinetic friction coefficient is much less than the static friction. Now coming to the case of fluid friction, these are actually forces which operate in liquids and gases also. Now these are, as we know, commonly called fluids. Anything which can flow. For example, compare the flow behavior of water and honey. It is just like our good old friends rabbit and tortoise, comparing their speeds. We know that honey is rather sluggish in its movement and spreads more slowly as compared to water. The following demonstration will illustrate this point. Now this is water spreading on a surface quite easily. And here I have marked the area over which the water spreads. Now this is honey spreading on the same surface but to a very less extent. So in comparison you can see the area of spread of water, and we realize that the speed with which the honey flows is much slower than that of water. Fluid friction occurs between fluid layers that are moving relative to each other. This internal resistance to flow is named viscosity. It describes the friction between layers of a viscous fluid that are moving relative to each other. Thus, such friction opposes the development of velocity differences within a fluid. It will be effective both between adjacent fluid layers as well as between surface of an object moving in the fluid, like ship in the sea, a man swimming in a river, etc. So this illustrates the frictional forces inside a fluid. So here we have an object moving in a particular direction either on the surface or inside the volume of a fluid, and the fluid friction opposes the movement like this. Different layers of the same fluid or different fluids. So one set of layers moving relative to another layer. So there arises the frictional forces. Now let us see what are the factors affecting the fluid friction. The fluid friction is found to be proportional to the relative speed between the different layers of the fluid. Also, the thinner the fluid, the lesser the fluid friction will be, and vice versa. And the frictional forces depend on the shape of the body moving through the fluid. So this aspect is related to what we call streamlining, and we shall explain this in slight detail later on. Also, the frictional forces vary with temperature, and also it depends on the surface area of the body, and therefore less area will be preferable so that the frictional forces can be minimized. Now what do you mean by viscous drag? Now consider the fluid flow along a cylindrical pipe like this. The fluid layer in contact with the inner surface of the pipe will be at rest. The fluid velocity increases towards the axis as you go from the inner surface of the pipe towards the center, and the flow rate will be maximum at the center. So these vectors represent the velocity starting from the surface of the pipe towards the center or axis, and then we once again cross the axis and go towards the other end of the pipe, other surface of the pipe, when from the center onwards the flow rate will decrease towards zero. So this means that there must be some force holding the fluid back, and this is exactly what we refer to as viscous drag. Now just like the coefficient of friction in the case of solid surfaces, we have also the coefficient of viscosity eta in the case of fluids. It is defined as the force of friction that is required to maintain a difference of unit velocity gradient. That means a difference of velocity of 1 centimeter per second between parallel layers of a fluid. The unit is usually expressed in poise or centipoise, or also Newton second per meter squared is actually equal to Pascal second. Let V1 and V2 correspond to the velocities of two parallel layers of area A, and suppose these are separated by a distance d. Then it is found that the force of friction will be given by F is equal to eta A into V2 minus V1 by d. That means the frictional force will be proportional to the area of the surfaces which are in relative motion with respect to each other, and the velocity gradient V2 minus V1 by, and the proportionality constant is what we refer to as the coefficient of viscosity. Consider the fluid flow along the pipe. Many times it is necessary to calculate the flow rate of fluids like water, petrol, cooking gas, etc. along the carrying pipes. The viscosity is an important factor deciding this characteristic apart from the geometry of the pipe. Usually we have cylindrical pipes. Now consider the fluid flow between 2 points A and B along the length of a pipe of radius r and separated by a distance L. So we have considering 2 points A and B at a distance of L such that the pressures at these 2 points are P1 and P2. Empirically we know that higher the pressure difference between the points, the flow rate will be higher. So if we raise the pressure at the point A, then we can see that the flow rate will be more. Also, a more viscous fluid will offer more resistance, which is designated by R, to the fluid flow, and consequently the flow rate will be smaller. The higher the viscosity, the flow rate will be smaller. So there is a sort of inverse dependence on the viscosity or the viscous resistance offered to the fluid flow. Therefore, one can write for the flow rate Q, that is the volume per second, the volume flowing a particular area of cross section per second, that is equal to some constant into P1 minus P2 divided by R. So this is the pressure difference, and R is the resistance offered by the fluid arising from the viscosity property. In such cases, we consider only laminar flow, wherein the paths followed by small volumes of fluids called streamlines are smooth and continuous. They are also parallel like this. So this corresponds to what we call the laminar flow of fluids. In contrast, we have the non-laminar or turbulent flow, which is characterized by non-parallel lines along which the fluid flows, and also sometimes eddies and swirls that mix layers of the fluid together. Now in the laminar flow, the fluid does not mix together, whereas in turbulent flow there is mixing of the fluid, and the flow is also irregular and chaotic in the case of the turbulent flow. Now the fluid flow is characterized by an important dimensionless parameter which is known as Reynolds number, which identifies the behavior of fluids based on attributes like viscosity or velocity of the fluid. Accordingly, the value of Reynolds number can be expressed as R is equal to rho Vd by eta, where rho is the density of the fluid, V is the fluid velocity, D is what is known as the hydraulic diameter of the pipe or tube or duct, whatever it is, through which the fluid flow occurs, and eta is the characteristic property, that is viscosity of the fluid. We can differentiate between laminar flow and turbulent flow with respect to this Reynolds number. So usually it is recognized that for laminar flow R should be less than 2100 or so, and for turbulent flow R should be more than 3500 or so. The intermediate region, that is from R is equal to 2100 to R is equal to 3500, is what is known as the transitional flow region. For such a laminar flow, we have from Poiseuille's law, R is equal to 8 eta L by pi R raised to 4, and therefore finally we can write for the volume flow rate Q is equal to K pi R raised to 4 into P1 minus P2 by 8 eta L. So therefore the flow rate is inversely proportional to the viscosity and directly proportional to the pressure difference. In order to match the proper units on either side, we choose K is equal to 1. Now there is a genuine question: can there be a liquid with zero viscosity? And definitely the answer is yes. And it is a unique liquid, namely liquid helium. Its viscosity is identically zero below a certain temperature, which is characteristic of helium. And the value of this characteristic temperature is 2.2 degrees Kelvin. This is known as the lambda point. And this phase of that liquid helium is called a superfluid. Zero viscosity obviously means an infinite Reynolds number from our earlier discussion, because it is inversely proportional to the viscosity. That means when the Reynolds number is infinite, or when the viscosity is zero, that represents the ability of the fluid to flow through fine capillaries without outward friction. There are some other special properties of the liquid helium, which include creeping up over walls of its container against force of gravity as a thin film, and possessing the highest thermal conductivity of all substances. Another important feature that fluids possess with regard to the property of viscosity is what is known as terminal velocity. So this refers to the movement of solid objects through the fluid. For example, consider a glass ball which is dropped into a liquid like honey or coconut oil. So that is a vertical motion of an object under gravity within a fluid. Now this motion is governed by what is known as Stokes law, which gives the viscous drag in this particular case equal to 6 pi r eta v. So therefore the net force is equal to mg minus 6 pi r eta v. So this will increase as v increases, obviously, as the particle or the object moves downward under gravity. its velocity will increase, and therefore the frictional drag, the viscous drag will increase, and therefore the net force will go on decreasing until finally at some particular value of V, one can see that obviously mg will have to match with this particular value, the viscous drag, and under that condition the net force will be 0, and thereafter velocity will be a constant because the acceleration is 0. So that particular value of the velocity at which the particle will move with constant speed is known as the terminal velocity. The most familiar example of this are raindrops in the atmosphere. So when they reach the earth, they will be moving with the terminal velocity. Now there are many examples of friction as a boon as well as a bane. For example, it is the frictional force which helps in walking or running and prevents us from slipping. Actually, absence or very little friction may be dangerous. For example, it is very difficult to walk on ice, but at the same time it is good for ice skating. Also, a moving vehicle stops when brake is applied due to the friction between the tires and the road. Also, friction helps to keep objects on surfaces. For example, furniture on the floor, a book on a table, etc. Okay, see, we can hold a glass of water like this in our hands. We can write with our pen on a piece of paper. We can sharpen our knife on an appropriate stone, or we can light a matchstick by rubbing against the side surface of the matchbox. So here this is a case of producing fire by means of friction. So in all these cases we know that it is the frictional forces which are operating and helping us to perform the works that are indicated by these pictures. Now, so these are some examples where the friction is a boon for the human beings. Now what about the bad side of the frictional forces? Of course, one common difficulty in almost all cases of frictional forces in action is the dissipation of mechanical energy into wasted heat energy. For example, tires of vehicles get warmer as the vehicles move. Also, moving parts of engines and motors get heated up and may get deformed. To sum up, friction is a non-conservative force. This we have already seen. So mechanical energy is being converted into heat energy. So friction is a non-conservative force. There is always possibility of wear and tear resulting in frequent replacements of components of machines, tires, etc. Now wear is the gradual removal of material at solid surfaces occurring as a result of damage caused by friction and or of course corrosion also will play a major role in this wear. And of course wear of the components will lead to loss of functionality of whatever equipment that component belongs to. Therefore, friction lowers the efficiency of machines, and no machine is 100% efficient because of the effect of friction. In a hypothetical frictionless machine, input would be equal to output, and we know that practically this can never be the case. Friction obviously causes an increase in fuel consumption of vehicles because of the loss of efficiency due to the frictional forces. Thus, a vehicle with better fuel consumption will have less friction. Vehicles with more wear and tear or less efficiency will have more friction and will need more fuel to operate. Friction also causes overheating of engines. This accelerates breakdown and decreases efficiency. The heat generated due to friction can cause expansion of materials as well. This will lead to mechanical instabilities which impact the functioning of the machines even more than the normal wear and tear, as this has a structural impact as well. With regard to the heat generated from friction, there is another common example, that of a shooting star. If a meteoroid gets close enough to the earth that it enters our atmosphere, the friction with air molecules heat it up and it begins to burn up and fall to the ground. This burning trail is known as a meteor. They are usually bright in color and leave beautiful trails of light in the sky. This is also sometimes referred to as a shooting star. Another important feature associated with friction is the creation of electric charges. Of course, this can be a boon as well as a bane. That is, when two insulating objects rub against each other vigorously, the transfer of free electrons takes place between these two objects. The object from which electrons rubbed off acquires a positive charge, whereas the object which gains electrons obviously will acquire a negative charge. This is one example in particular, that is the rubbing of an ebonite rod with a fur. So once you separate the ebonite rod and the fur, you can see that both carry charges. The fur loses electrons and becomes positively charged, whereas the ebonite rod which gains these electrons will be negatively charged. Similarly, this will be a very common experience for many people, that if you comb the hair, especially in dry weather, then after combing you can see that the comb will be electrically charged. In fact, the comb will be negatively charged and the hair on its part will be positively charged. Now if you bring the charged comb near, say, small paper pieces, then you can see that the paper piece gets attracted towards the comb. In fact, charging by friction has been one of the earliest methods of producing electric charges. Well, one should not say producing electric charges, it is rather separating the electric charges, because normally the positive and negative charges are found in a bound state. So what we do by friction is just separating these positive and negative charges. Now there is a particular branch of science which deals entirely with the science as well as engineering of interacting surfaces in relative motion. That is called tribology. The word tribos means to rub. So anything connected with rubbing of the surfaces and the subsequent effects will come under the field of tribology. So it includes naturally three subjects: friction, wear and lubrication. Hence it is an interdisciplinary topic combining physics, engineering, metallurgy and also chemistry. So also wear, because that can arise from corrosion, which belongs to the chemistry branch. Now what are the ways to reduce or minimize effects of friction? Of course, we can't imagine a world absolutely free from friction. That is, completely smooth surfaces are impossible to achieve in the real world. What we can do maximum is that we can hope to reduce and try to minimize the effects of friction. These are some examples where we take steps to reduce the friction to the minimum possible level. For example, in the carom board, we usually sprinkle fine powder so that the striker and the coins will move with less friction and they will move faster.
In this context, do not forget that there are situations where you would like to increase the friction between surfaces rather than decrease. For example,
the soles of shoes are grooved so that we get good grip with the ground. The same is the case with the tires of vehicles. They are treaded so that we will get firmer grip with the road. When a few drops of oil are poured on the hinges of a door, we know that the door moves more smoothly. Similarly, a bicycle and a motor mechanic usually use grease between the moving parts of these machines so as to reduce the friction. In all the above cases, we want to reduce friction in order to increase the efficiency. So what are the different ways to reduce or minimize effects of friction? The first is obviously making the sliding surfaces smoother. By smoothing the sliding surfaces, we could reduce interlocking of the heels and tails, and thereby the friction can be reduced. Now what are the methods of smoothing surfaces? Grinding, using a hard substance, and finally using fine grade sandpaper. Or we can use chemical etching to eliminate surface imperfections. For this we can use a harsh chemical treatment in order to remove the surface imperfections. So that way one can make the surface smoother. Another is the application of lubricants. This will lower the friction, minimize heat generation as well as ensure that the sliding is smooth. A suitable lubricant, say a thin film of oil, is created between the moving parts of a machine. What does the lubricant do? The lubricant separates the two touching surfaces just a little bit, and the quantity of interlocking is considerably reduced thereby. That means the relative movement becomes smoother. Typically, the lubricant to surface friction is much less than the surface to surface friction in a system without lubrication. So that is how the lubricant acts to reduce the frictional forces. The use of lubricants has been a very ancient practice. For example, the Egyptian pictures dating back 4000 years show the application of lubricants to reduce the friction experienced in dragging heavy monuments. Now in our own body we can appreciate the fact that at the joints there are lubricating fluids. For example, the knee joint, the fluid inside the joints of two or more bones protecting the connecting surfaces of the bones is called a synovial fluid. What is the function of this fluid? It enables the joints to avoid friction and to provide smooth functioning of the associated bones. A second function of this fluid is to protect the bone heads and cartilages from wearing out and to repair them in time. Lubrication also helps prevent excessive heating of moving components. Both gas and liquid lubricants can be used to transfer the heat. However, liquid lubricants are much more effective on account of their high specific heat capacity. Invariably, the liquid lubricant is constantly circulated to and from a cooler part of the system so that the cooling will be more efficient. The lubricants actually occupy the clearance between moving parts through the capillary force, thus sealing the clearance. This effect can be used to seal pistons and shafts. Now, another important method of reducing friction is by using rolling in place of sliding wherever possible. So, for example, if we want to slide an object along the ground, well, we can do it, but we will have to push harder as compared to the situation when we fix wheels on the underside of the object and try to push it. Actually, the wheels will roll and the rolling friction is less than the sliding friction, and therefore we can move the object with relatively less effort as compared to the sliding case. Also, ball bearings can be used. The streamlined design of the sliding body will also help in reducing the friction. This is especially true for friction in fluids. It allows the sliding body to travel through the medium with the minimum amount of resistance possible. What do you mean by a streamlined body? Streamlining is the process of shaping the object properly so that the fluid flows around the object in such a way that the resistance applied to the object will be minimum. So, for example, the particular shape of the body results in the fluid flowing like this instead of flowing like this and offering larger resistance to the flow of the body. So, it is the particular shape of the body which avoids direct resistance on the surface of the body by the fluid. So, the streamlined designs have often rounded shape in front as well as narrow throughout the back. So, this is one way in which the streamlining can be effectively done. In fact, see, we are actually copying the streamlined bodies of fish and birds in order to achieve low friction. The ships feature streamlined shapes that aid in reducing friction well within water or liquid. Also, the bodies of rockets, automobiles and airplanes are typically streamlined to decrease friction with the air. So, the airflow will be along streamlines so that the actual frictional force offered to the object moving is minimal. Now, finally, we come to an important device called the inclined plane. In fact, no treatise on friction will be complete without a discussion on this mechanical device. So, here we see a man pushing up the cart so that the load can be brought up with ease. Now, the inclined plane is one of the 6 simple machines. It is also called a ram, and it is primarily used as an aid for raising or lowering a load as shown in this figure. It is useful because the inclined plane can raise heavy objects against the force of gravity without the object going vertically up. For example, loading goods in trucks, ships and planes. It's a common belief that ancient Egyptians used the inclined planes to carry heavy stones to build pyramids. We can see the inclined plane being used as lights in children's parks. Also, escalators in railway stations and airports and slanted conveyor belts in factories and industries are forms of an inclined plane. See, this is the aircraft evacuation slides which allow people to rapidly and safely reach the ground from the height of a passenger airliner. Other common examples: a sloping road connects a roadway to a bridge or overpass. A ramp is used instead of a staircase for wheelchairs and shopping carts in departmental stores, etc. Of course, there is a trade-off with the simple machine, because if the slope is gentle, a person has to push or pull the object over a longer distance but with little effort. In contrast, if the slope is steep, a person has to push or pull the object over a comparatively shorter distance, but the effort will be comparatively more. So that is the trade-off I was talking about. Basically, the inclined plane comprises of a sloping surface, maybe a wooden plank. It does not have any moving parts, neither does it move by itself. So here we have a typical inclined plane. We have a wooden plank supported at one edge by another wooden plank of length h. Capital L is the length of the inclined plane, so that it makes an angle theta with the horizontal surface on which it is resting. So tan theta will be given by h by L. In a physics teaching lab, The inclined plane is used for illustrating and demonstrating the important characteristics of the functional forces and also to experimentally determine the coefficient of friction. This is our inclined plane, and the angle between this top plane and this surface, that is this angle, is the angle of the inclined plane. I am going to use this as my object. Now this is a Rubik's cube. I am going to use it as my object, which I place on the inclined plane. Now you can see that at this particular angle, my object doesn't slide down. Now suppose I increase the angle of the plane like this. It doesn't move. I go on increasing the angle, and when a particular angle is reached, you can see that it slides down. So I am going to show it once again. So it starts sliding down at a particular angle. So this is that angle. Now suppose I keep the plane at an angle which is slightly less than the angle at which the object starts sliding. Okay, this is the angle. So I keep a slightly less angle. So it doesn't slide down. Now what do? I just push the object. Now it slides. So that means once it starts sliding, the friction is less than what it is when the object is not moving at all. Now I replace the Rubik's cube with another object, namely a steel glass. Now let us repeat the experiment. It doesn't slide now. I start increasing the angle and it starts sliding. You can see that this particular angle at which the steel glass started sliding is less than the earlier angle which was to be used for the Rubik's cube. Now coming to the theory of the inclined plane, we consider only the free sliding under gravity. So we have the object sitting on the inclined plane. The gravitational force is the weight of the body mg. Now we can resolve this into two components, one along the plane and the other normal to the plane. So the parallel component is mg sin theta and the perpendicular component is mg cos theta. So the normal reaction n in this case will be equal to the component perpendicular to the plane, that is mg cos theta. So the frictional force Ff will depend on mg cos theta. So actual frictional force will be mu mg cos theta, mu times the normal reaction. So therefore the net force acting on the object in order to slide it is equal to mg sin theta minus mu mg cos theta. That is the parallel component of gravitational force less the frictional counterpart. So starting from very low values of theta, that means almost starting from the horizontal direction. Suppose you go on increasing theta, then up to a certain angle the friction force opposes the force due to gravity and the net force is 0. At the moment of sliding, the angle is, let's say, theta 0. Then up to that point, mu is the coefficient of static friction, mu st. Hence we have mg sin theta 0 minus mu st mg cos theta 0 is equal to 0, and therefore mu st is equal to tan theta 0. This is the angle of friction, also sometimes called the angle of repose. So it is the maximum angle at which a load can rest motionless on an inclined plane due to friction without sliding down. Therefore, by measuring the angle of friction, the static coefficient of friction can be calculated. This is found to be independent of the weight of the object and depends on the nature of the two surfaces. Now here we have a particular experiment carried out with the inclined plane. So we have three inclined planes. One is made of concrete, the second is made of wood, and the third is made of glass. Now from experimental calculations, we know that mu1 is greater than mu2 greater than mu3. Now what we do in this experiment is we use the same let's say wooden block and we keep the inclined plane at such an angle that sliding just starts in the three cases, and we measure the distance which the object traverses in a given time t. So the concrete has the maximum friction of all three and the glass has the minimum friction of all three. So therefore you can see that in the same time the object on the glass inclined plane will travel more distance as compared to that on the wood inclined plane, and that also will be larger as compared to the object on the concrete wooden plate. So therefore mu1 greater than mu2 greater than mu3. So we have just the reverse case for L1 less than L2 less than L3. So therefore this particular experiment illustrates these features of the frictional forces. First of all, the difference in the frictional forces of different materials, and also the angle at which the motion just starts. That also will be different for the three cases.
I will end this video at this point.
If you like this video, kindly click on the like button and share with your friends and relatives, and also with your different groups. If you are not already subscribed to my channel Murali's World of Physics, kindly do it now. And please don't forget to click on the bell icon so that you will receive notifications in future about my upcoming videos.
I'll be back soon with yet another video on basic principles in physics. Till then, goodbye.